Okay, so we have these questions. Got the vector from here to here, and then the vector from here to here. And everybody does a good sketch, with something like that. Got a vector here, and got a vector goes right here. And you try to find, among other things, the angle between them. This is V1. This is V2. V1 equals, well, from -4 to 2 is 6. So you got to go 6 units this way to get from -4 to 2, so it's going to be 6. And I'm not going to draw all the triangles and projection lines, but I think everybody knows how to do this. From 6 to -2 is going to be -8. And of course, you got 0 in there. And if you left the 0 off when you were doing the thing in the XY plane, that's fine, because it won't have an effect. But I'm going to go ahead and write them in 3 dimensions, okay? Because we are going to end up doing a cross product, so we'll just keep. The picture can be drawn in 2 dimensions. We understand it's in the XY plane. The second vector is V4, 10, 0. Okay, I got it right. Okay. Okay, so we want the angle. So V1 dot V2, magnitude of V1, magnitude of V2, times the cosine of theta. So theta is the inverse cosine of V1 dot V2. Here the magnitude of V1 times the magnitude of V2. That's a simple calculation. Okay, just solve for the cosine. You're just going to divide both sides by the magnitudes. You're going to get this. And then to find theta, you do the inverse cosine. Okay. And that's going to then be the inverse cosine of V1 dot V2. So I'm not going to write out the details, but it's 6 times 4, which is 24. And -8 times 10, which is -80, which gives you -56. Over. And actually the angle between, well, that's what we'll do. Magnitude of V1 is going to be the square root of 6 squared plus 8 squared, right? Times the square root of 4 squared plus 10 squared. Okay. Now, the square root of that is a little less than 11. Square root of that's about 10. So it's got like -56 over 100 and I'm losing my numbers again, 110. Be the inverse cosine of about -0.5. Okay. And that would be close to 120 degrees, which doesn't seem quite right. Pictures I'm seeing look like they're relatively to scale. You can all be like 60 degrees, but the dot product is definitely negative. Unless I did something wrong. 4, 10. Okay. 4, 10, and 6, 8. That's got to be an acute angle. So it might be something wrong there, but I can't see it. You're getting a negative here, and that gives you an angle greater than 90 degrees. And there's no question, I think, unless I've got a sign wrong somewhere, which is entirely possible. Okay, anyhow, that's how it's calculated. Okay, and I'm not too worried about the numbers. The process is you use the dot product to find the angle. Okay, and that's very basic. That's pre-calculus level. Okay. Okay. Unit vectors, also pre-calculus level, so make sure you get it. You can check pre-calculus text. You can check on it. I did mention that your text does have a whole chapter on vectors. Chapter 2. First 4 sections, I'm not talking about much. They're covered by what I've asked you to do, and that should be covered by what you know from other courses. And if it isn't, you're going to have to dig it out, but you're welcome to ask questions about anything. Okay? Because we can't spend time learning pre-calculus. Okay? We can't get through this course if we do that. The course is way too important to mess with that. Okay, these things will gradually become important in this course, some very soon, some a little bit later. Make sure you get this stuff down. Make sure you can do the problems that I've given you. You only had 2 days to do it, but I'm going to give you some more problems to do next week and something else. Okay, so make sure you spend enough time to get those done. If you have questions, you can ask AI if you want to, but don't ask them to do the problem for you. Ask them to explain what's going on. But more beneficially, use the stuff I told you last time. Everything you need is there. So make sure you can pull all that together. Okay, so unit vectors, and they're going to be important real quick, and it's real easy. Okay. V1 is, I need to put an arrow if I'm going to use this notation. It's compact, so I'm using it. This notation. I can't use this notation in anything on word process because I can't put an arrow over things. There's a way, but I'm not going to mess with it. I got to get these things out. But usually I've been boldface. Okay. And vectors would be indicated not with an arrow, but with a boldface. So if a bold-faced ordered pair or ordered triple, it probably means it's a vector. Look at the context. You'll be able to figure out whether it really should be or whether I accidentally bolded it. Okay. So V1, -2 to V1 over 10 is 6, -8, 0 over 10, which is 0.6, 0.8, -0.8, 0. Right. And then U2 and that's going to come out approximately 0.36 0.90. That's very approximate. I could go another decimal place and maybe get a little closer, but that'll do for right now. And these are vectors, we have to have arrows on. Okay. Now, we want to find V1 cross V2. I'll use the IJ notation just like I did before. IJK notation in this case. It's going to be 6I minus 8J. And there's no K, so I don't have to write out a K component. And 4I plus 10J, which equals then 24I cross I using the distributive law plus 60I cross J minus 32J cross I minus 80 J cross J. Now, that's what you write out if you write out the whole distributive law. If you want to shortcut that a little bit, since you know that I cross I is 0, you know that this cross with this is 0, you don't have to write it out. You don't have to write negative 8j times 10j or cross product. Okay? You just need this and this. And that's 60k minus 32 times negative k. Right-hand rule on I, j, and k. You don't need a determinant. Sometimes the determinant is longer than what we're doing here and less confusing. If each of these vectors has a component that's 0, it's easier to use the distributive law than it is to use the determinant. Okay? But you can do it either way you want. You save yourself a little time. And also, if you prove things, a lot of times the proofs use this kind of notation. Okay? So it's important to understand it. I really have a preference for doing the distributive law when each vector has a component of 0. Okay. That's my personal preference of it. You can do it any way you want to. If you're in a hurry, this is quicker. Okay. In this case, if you do it for all three have non-zero components, both vectors have 3 non-zero components, that determinant is easier for most people. Okay, comes out the same, doesn't matter. The angle of V1 cross V2 with V2 is the inverse cosine of this. If I dot V1 cross V2 with V2, I know what I should get, and it doesn't look like I'm getting that, so it's screwed up here. Oh, never mind, no. It's 0. V1 cross V2 is just a multiple of k. If I dot 92k with 4i plus 10j, I don't have an I component to match up with this I component. I don't have a j component here to match up with this j component. The dot product is 0, and that should be totally obvious, okay? And of course, probably need to do some more calculations to see that. I'm just saying it's 0 and it's obvious if you just write these things out and do the rule for dot product, okay? And you kind of need to discover that yourself, so I'm not going to point out the details, just advise you, make sure you understand why that's 0. I just said it. But write out this dot with this and see what the rule gives you. Okay. Matter of fact, I'll even go so far as to say we're doing 4i plus 10j plus 0k dotted with 0i plus 0j plus 92k. Gives you 0 times 4, 0 times 10, 92 times 0. All zeros. Okay. ponder that if it wasn't obvious to you. Okay. And, you know, I understand, you're probably a little rusty in this stuff, and maybe you didn't even learn a lot of this stuff because of deficiencies in the courses you had before. And maybe you did learn it, but you forgot it, in which case you should think about how you learn things. Okay? Try to learn things so you retain them, not just so you get the right answer when you need it. Okay. Now I want to switch gears. Well, never do get that in the right place. There it is. So what have I drawn a picture right here? That's fine to record and talk about. So this line is the line x equals cosine theta. This line is the line y equals sine theta. If you want to read off the values, and you got a scale from the graph. And incidentally, when you first said this was a unit circle, I took that as a great compliment because it's pretty elliptical, but I meant it to be a circle. Okay, yeah, it's a little too fat. Okay, but anyhow, it's still reasonably okay. And even if it's an ellipse, you can make the estimate. If the scale here goes from -1 to 1, and the scale here goes from -1 to 1, I don't care how flat or skinny it is, it's going to give you the correct, it's going to give you reasonable estimates. So what do you estimate the cosine of this angle to be? I'm not sure where we stopped, but somebody estimated that the cosine would be 1/2. If said -1/2, I think you wouldn't be too far off, but here's where x equals 1/2, and that doesn't have anything to do with this line, except maybe gives you a better picture of the scale, so it's worth doing, okay? But it's not an estimate of the x coordinate here, which is between 0 and -1. This is a unit circle. So x is 1 here, -1 here, y is 1 here, -1 here. And you're going to estimate within that context. Okay, so if x is -0.63 here, then, you know, maybe negative, around -0.6, -0.7. I think it's actually probably a little closer to -0.7, but I didn't want to be too accurate. Okay. I'd have maybe gone -6.8 or something like that. I could make that 3 into an 8, but I'm not going to do that. Okay, now y equals sine theta. Okay, which equals what? What's the y coordinate here? Well, 0 is here and 1's here. Now it's a lot closer to 1 than it is to 0. You need like 1, 2, 3, 4, almost 5 of these. So I'd say that's about 1/5 of the distance between 0 and 1, which would make this estimate about 0.8. Okay. And that's very approximate because my circle isn't even all that good. And my y-axis isn't and all that great. Okay, well, it turns out, and that was an honest estimate. This is a reasonably honest estimate. And I'm glad I went with a lower estimate because 0.6 squared plus 0.8 squared is 1. Okay. Now sine squared theta plus cosine squared theta has to be 1 by this picture because there's the length 1. And this could be represented maybe as a vector. And that vector is cosine theta I plus sine theta j. which we then say, I think it's approximately negative 0.63 I plus 0.8 J. Now, magnitude of cosine theta I plus sine theta J is cosine theta I plus sine theta J dot cosine theta I plus sine theta J, which is cosine squared theta plus sine squared theta, which everybody knows from childhood to be 1. Now, of course, it has to be 1 because this circle has radius 1 and this vector has length 1 because it goes from the center to the circle. Okay. So it has to be 1, which means this isn't quite right. My estimate and incidentally, the magnitude of this is the square root of this dot product, so it's the square root of this, which is still 1. Okay, so this would be 0.63 squared is about 0.4. Or 1.04, which is approximately 1.02. If you plug those numbers into the calculator, I think you're going to be pretty darn close to 1.02. These are pretty easy to estimate. Okay, you're with me. It's pretty easy to estimate. I think I estimated it right. So, if you want to estimate the sine and cosine of some angle, draw a picture of that angle, draw the projection lines, and estimate the sine and the cosine, get your estimates, and see if they satisfy the Pythagorean theorem within reasonable limits. Okay, that's off by 2% there, basically, on the magnitude of the vector. If I'd have gone to 0.68, it would have been worse. Okay, I'd probably been around 1.04, 1.05, which looks good, but not particularly good. Still, if you want to understand sines and cosines, do what I said. Okay. Now, we're not here to do elementary trigonometry because that's very elementary trigonometry of functions. Okay, now we just had a question that this vector, well, the vector I is the vector 1, 0, 0. Vector J 0, 1, 0, because the way they would define unit vector in the direction of the x-axis. One unit in the direction of the x-axis, nothing in either of the other directions. Okay, so that's a good observation. Then I say, you know, when you're doing the problems, I'm not sure how I made the transition there, but you need to work through the problems I gave you. There's a kernel of a whole lot of the stuff that we're going to cover in the first couple of weeks of the course. Okay, and it's stuff that's necessary to understand. And I say you can work through the first 4 sections of chapter 2 in your text, which I consider to be review that we do quickly, like in one day, which we already did. I will say work through those problems based on what I gave you in class. Okay, to the best of your knowledge, but don't let yourself get too bogged down. If there's something you don't understand, take a look at your book. It's all there in the first 4 chapters, everything I told you. And basically everything in those not first 4 sections of chapter 2, basically everything in those first 4 sections, I think, was pretty well covered implicitly by what I did in class. And one of the things you want to do in learning mathematics is bring all the numerous things you need to understand down into one little bundle. Okay, so what I gave you is a fairly small bundle, but it's a bundle of something that theoretically you covered in pre-calculus and used in your calculus course when you were doing trigonometric functions. If you did trigonometric functions in your calculus course without thinking about this, you weren't thinking as well as you could have, okay? Because this is something that brings everything down into just one simple little picture. And it represents everything that you can do with trigonometric functions. Okay, well, at least with sines and cosines and tangents. Get into the reciprocals, things get a little confusing. But still, it just comes down to this. It doesn't come down to punching buttons in a calculator. It doesn't come down to doing manipulations on a paper that you can't relate to this. Although if you do those manipulations, that's still an accomplishment. I'm not denigrating that at all. But seeing it in terms of this, that's where you understand it. Okay. Now we're taking way too much time with this. We've only got a half hour left. And I need to cover the whole topic of parametric equations. Still, this is going to help. The first set of parametric equations I want to give you is x equals cosine t, y equals sine t. T goes from 0 to 120 pi. So what's the graph of this system of parametric equations? Well, you could start by letting t take values, let's say 0, pi over 4, pi over 2, 3 pi over 4, 2 pi over 4, 3 pi over 2, and 2 pi. As you know, with the cosine and the sine, I hope you know, are going to go through a complete cycle. This theta goes from 0 to 2 pi. Theta being measured in radians around the circle. Okay? And if you don't understand radian measure, get used to it as quickly as you can, because that's what we do in mathematics. Okay? You certainly didn't do your calculus 2 derivatives in degrees. Okay? And integrals are so forth. Okay, so we can put down cosine t. Well, I'm just going to put down x and y. We're going to get a set of x's and y's. If t is 0, you can look at the picture and see that the cosine is 1. The cosine of t, t would be the angle. The angle is 0. You're at this point. And the y coordinate is 0. That's this point on the circle. Pi over 4 is this point. Now this would be square root of 2 over 2, square root of 2 over 2, right? That's about 0.71. 707. And I'm not sure where it goes from there. Can't do the Taylor expansion of that one in my head. The numbers. Okay, so anyhow, pi over 2. So I'm not going to belabor it. You look at the picture. Pi over 2 is this angle here. That puts you at y equals 1, x equals 0. And then you have negative 0.71 and 0.71. And then you have negative 1, 0. And then you have negative 0.71, negative 0.71. And then you have 0, negative 1. And I left out 7 pi over 4. And you have then 0.71, negative 0.71, 2 pi gives you 1, 0 again. And you're back where you started. And then you keep going around the circle. How many times did you go around the circle? This set of equations goes around the circle 60 times. Because every time around the circle is 2 pi radians. Again, if that's not familiar, you're gonna need to dig it out. And it won't hurt you to do that. Okay. So now we have this table, and we usually don't make a table. We usually use the behavior of the functions. I can start sketching these points, and I've got 1, 0. I'm just going to skip 1, 0 to 0, 1, negative 1, 0 to 0, negative 1, just using this point, this point, this point, this point, and then back to this point, right? So the question is, how do we get from here to here to here to here? Do we go along a straight line? Well, one thing we might observe if we're doing this in a little more sophisticated way than making a table is by saying that, okay, I know that x squared plus y squared equals 1. X is a cosine, y is a sine, so the sum of the squares is 1. Okay. Which means the distance of every point from the origin has to be 1, which means we're on the unit circle. Now, if I do the 0.71 would be about here, 0.71 would be about here. And then about here, negative 0.71, 0.71. And then down here, negative 0.71, negative 0.71. And then here, so I'd have these points. And now I can connect them. And by darn, they make a pretty good circle. Within the inaccuracy of my, or the inconsistencies in my distance. Okay. And we go around this circle one time every time t changes by 2 pi. And we're going around the circle in this direction. So the graph goes around the unit circle. Counterclockwise. Every time t changes by 2 pi. And now I have the universal question of whether all this is actually there on Zoom. Zoom has a banner across the bottom. I never know if it's covering the bottom or not. So now I've got a little too high, but it's all right, it's all visible. Okay, so does that make sense? You can see that from the table. You can see that if you understand the sine and cosine. And you can see why I started with that unit circle and kind of emphasized some of its characteristics. Okay, well now, what if we have x equals 2 cosine t and y equals sine t? What do you do now? Well, you could change the table. You could double all the x's, right? That should be pretty obvious what happens is your x's are going to go from -2 to 2, and your y's are going to go still from -1 to 1, right? So what you're going to get is an ellipse. The easiest way to draw the graph of an ellipse, if you just want to do the shape of the ellipse and you know the major and minor axes, is draw a rectangle and then draw something that's kind of like a circle, the tangent for the rectangle. Now, my 2 here was too small compared to this 2, so it's a little lopsided. It's not a good ellipse, but you understand what's going on. Okay. Now, is the distance from the center always the same as you go around this? Well, no. We're certainly closer to the center here than we are here, right? And at other points, our distance from the center keeps varying. So what's our distance from the center? Well, it's the square root of x squared plus y squared, which is the square root of cosine squared, nope, sorry. It's 2 cosine t, so it's going to be 4 cosine squared t plus sine squared t, which could be written as the square root of 3 cosine squared of t plus 1. And why is that? I take one of these cosine squareds and match it up with the sine squared to give me 1, right? So I keep 3 cosine squared out here, but then that leaves me a cosine squared plus sine squared, which is just 1. That's probably the simplest expression. Okay. Okay, so another question. I'm just trying to get to some of the main questions we ask about parametric equations without getting into too much detail on how to graph them and so forth. We'll probably have to talk about that for another day. Give you just a little more time. We can't spend any more than just Tuesday before we get into the course, because we're not really in the course. We're into review. And then, okay, when I say the chapter in parametric equations is review, well, it's not all review. First few sections are review of what you should know. Okay, so I'm trying to hit that quickly and give you the most basic and most important ideas and operations to use parametric equations. It's going to take you a little while to sort it out. Okay, I want you to spend as much time as you can getting this stuff together. You will be glad for it when we get to the end of the semester and you have to do the integral theorems. Okay, because that's where the course really gets tough. It's toward the end. Everything before that is, if you know your calculus, it's pretty manageable. There's a lot of it, so you're going to have to spend some time. As I've told you before, this course is the language of most of engineering past this point, and also gives you a picture that you can use if you happen to be like in data science to understand certain things about data structures and multidimensional spaces where most of your structures live. Okay. Okay. So what I'm saying, basically, don't let this overwhelm you right now. But sort through it and understand you're going to have to understand it all pretty quickly. Okay. Probably won't nail everything before Tuesday. You want to get as many of the basic ideas as you can. Okay. So, talk about the distance from the center. The rate at which the distance from the center changes with respect to t is the derivative of this expression with respect to t. This is the distance. The rate at which the distance changes with respect to t is the derivative, because that's what a derivative is. Now, people often, maybe even usually, come out from calculus not really knowing what a derivative is, because you get so lost in the process of learning how to do derivatives and integrals and all the tricks and stuff. There's a lot of it. It's understandable. But what's a derivative? It's a rate of change. It goes back to the difference quotient. F of t plus delta t minus f of t divided by delta t. Take the limit as delta t goes to 0. If you've been thinking calculus without thinking that, you need to start thinking that, because we have to do it now in multiple dimensions. Okay? It's the limit. And you want to see this now because you're going to see it for multiple variables within a few weeks. Okay? That's the fundamental thing that underlies all the first semester calculus. Okay? It's fundamental, it's basic. You need to understand it. You need to go back and review it if necessary. F of t is your distance function, right? Because right now we're talking about the rate at which the distance in this ellipse changes with respect to time, or whatever t happens to represent. Such as the derivative with respect to t of this expression, which I didn't write very well here, so I've got a little arrow indicating that there's a neither. Okay, simple derivative, you got to use a chain rule. Take the derivative of 3 cosine squared t plus 1, which is going to give you 6 sine t cosine t, negative 6 sine t cosine t. And then it's over 2 square root of this. So you're going to have 3 sine t cosine t over that square root. If I did that right in my head, I'm not going to write it out. You need to know how to take derivatives. And if taking that derivative is challenging to you at this point, you probably need to practice taking derivatives so that later, when you really have to be able to get them quickly, you can do it and not stumble over derivatives when you're trying to understand something else. Okay? Taking derivatives with the basic rules and the chain rule. That's just a skill we have to assume in this course. So if you got to get better at it, you know, I'm laying a lot on you, but I'm just telling you, the better you get at it, the less you're going to stumble later. Okay? And I'm often a little surprised at how people don't even seem to remember the chain rule a few months after having taken 2 semesters of calculus. Okay? A lot of people do remember. Maybe all of you do, maybe most of you do, but you just can't live without the chain rules of calculus in a lot of ways. Okay. And again, a good way to review the chain rule would be ask AI, can you explain the chain rule? Get an explanation, you don't understand, say, I didn't understand that, can you explain it again? It's a sure, there's no explanation. Probably got, you know, multiple explanations that it could give you because it can be explained in many different ways. Okay, one thing that I'm not sure how the accessible AIs are with giving you graphs and pictures. They were pretty bad back in the days a year ago, which was like a century ago, as fast as AI is developing. Okay. And of course, you got books. You got OpenStax books. You got OpenStax books for Calculus 1, Calculus 2, and Calculus 3. Okay. Maybe you've got a book that you used in calculus. Okay. Now, one big deal. Okay. So let's just say we're on this set parametric equation. Okay. We have now I will introduce the term R or a notation R of T. And the best way to explain that is just to try to do a little better graph than I did last time. I like to draw my rectangle so that I'm always gonna, then I don't, always gonna kind of get the tangent line where it ought to be. I always get the curved tangent to the rectangle at the vertices. Okay, now that one's a little lopsided in this direction, so I'm hopeless, but there it is. Okay, and here is a typical R of T, and I'm already sorry I drew it there. I'm thinking ahead of what I'm going to do next. Here's R of T. And here is R plus B T plus R of T plus delta T. Okay. In other words, here's R at some time, and here's R a little time later, where we generally regard a delta T as a little quantity, but not always. But in this context, we'll regard it as a small quantity because we're going to be taking a limit as delta T goes to 0, as we do with derivatives. Okay. So difference quotient, which I'll be introducing in my pre-calculus class within a few weeks, because it is pre-calculus, and if you were through pre-calculus, it didn't see the difference quotient fairly frequently, there's a deficiency in that course. I'll say that without reservation. Not preparing for calculus if you haven't seen a difference quotient and understood the idea of a rate of change, which is why people come out of calculus courses not knowing what calculus is all about. Okay? Because they're always struggling against the deficiencies of earlier portions. As you'll struggle with deficiencies in this course when you need it. Okay? At some point. Okay. Every course has its deficiencies. But not emphasizing the difference quotient is one I just can't bring myself to respect. Okay. Okay. So what does this mean geometrically? Let's just get them out of the picture. Here's an R of T. And here's an R of T plus delta. I'm going to try to make one important point here. Now, can you draw me the vector for this numerator? Where is the vector? R of T plus delta T minus R of T. Am I killing you yet? My job.
Now,
I don't wanna
probably
kill you,
killed
but-
me semesters